welcome to the next video. This is going to be a review of the semester. So we're just going to go through a bunch of problems, and hopefully that will help you for the final. Okay? So on page 23 of the textbook, let's look at number 12. So you need your textbook for this. Okay, so take out your textbook, and we'll go to certain pages and certain problems, and we're going to do. Okay, so on page 23, number 12, it says use Venn diagrams to verify the following statements. All right, so we're going to use Venn diagrams to verify the following statements. So statement A is A intersection B prime is equal to A prime union B prime. And so this is one of De Morgan's laws. Okay? And so we're just going to draw a Venn diagram of each set. And if the Venn diagrams are the same, that verifies that the sets are the same. Alright, so the Venn diagram of A intersection B is that. That's A intersection B, right? So A intersection B complement is just everything outside of that set. So here, outside the shade region. So here's A and here's B. If that's A intersection B, so this is A intersection B, okay, then everything outside, everything other than that is the complement of the set. Okay. So I'm just going to shade in everything outside of the intersection. And this is A intersection B complement. Okay, so that's the Venn diagram of A intersection B complement. Now, if you look at the Venn diagram, so here's A and here's B. If you look at the Venn diagram of A complement, it's everything outside of the circle A. So that's everything outside the circle A. If you look at B complement, it's everything outside the circle B. Right? Okay. Pretty simple. Okay, so A complement is everything outside the circle A. B complement is everything outside the circle B. And so the Venn diagram for A complement union B complement is just shading in anything that's shaded in either in this picture or that picture. So for this picture, you shade everything outside of A. Okay. So that's everything outside of A for that picture. Now in addition to what's shaded there, we shade in whatever else that isn't shaded in yet from this picture. And so that's this stuff here. So now this is A prime union B prime. Okay, and so the Venn diagram for A intersection B prime is the same as the Venn diagram for A prime union B prime. And so since these are the same, right, so since this is the same as that verifies that those two sets are equal using Venn diagrams. All right, so that's 12A. All right, let's do 12B. All right, 12B. So for 12B, it's A intersection B union A intersection C is equal to A intersection B union C. So we're going to use Venn diagrams to verify this equality of sets. So if we draw the Venn diagram for A intersection B union A intersection C, then if we have set A here and we have set B here, then A intersection B is that, and then union A intersection, oh, this is A, sorry, that's A, B, and C. Okay. This is set A, this is set B, and that's set C. Okay, so A intersection B is this set. That's A intersection B. And then you union that with A intersection C. That includes that. So that's A intersection B union A intersection C. Right. So now, let's show the Venn diagram for, and you could call this the universal set U. Or X, so in our case, maybe set S or U, you know, whatever. And so, or let's say you had, you have the set A, you have the set B, and you have the set C, all in the larger set S. So if you have B union C, that's what's in circle B or C. And if you take the intersection of either of those circles with A, you get this, right? This is the region in B union C that's also in A. It's the same as that picture. So this is the Venn diagram for A intersection B union C. And so this Venn diagram is the same as that Venn diagram. And so that verifies that these two sets are equal using Venn diagrams. Okay, so that's control B. Okay, so let's control A and control B. So let's look at another problem. So next is page 40, number 28. So page 40, number 28. Right. So page 40, number 28. Let A and B be events with P of A, this is number 28. P of A is equal to 5/6 and P of B is equal to 1/3. And they want you to show the following. So let's show part A, which is that 5/6 is less than or equal to P of A union B less or equal to 1. Okay, so let's show that. Well, this inequality, this is just from the fact, the probability of any E probability of E is less than or equal to 1 for any event, right? For any event E. Right? The probability of any event is always at most 1. So the probability of A union B is definitely less or equal to 1. So we're good there. Okay? Now, A is a subset of A union B. Right? The set A is entirely contained in the set A union B. That implies that the probability of A is less or equal to the probability of A union B. If you have a set that's entirely contained in another set, and the probability of, if you have an event that's entirely contained in another event, and the probability of that event is less or equal to the probability of the other one. Okay, so you would have E1 is a subset of E2 as events. That would imply that the probability of E1 is less than or equal to the probability of E2. So that's what's happening here. A is a subset of A union B, implies P of A is less than or equal to P of A union B. That implies the probability of A, which is 5/6, is less than or equal to the probability of A union B. And so that confirms the first inequality. Alright, so this is the argument for the first inequality being true, and the argument again for the second inequality being true is from the fact that the probability of any event is at most 1. And so the probability of the event A union B is definitely at most 1. Alright, so that's part A, and there's other parts, but we did one of them here. So that's page 40, number 28. Okay. So that's page 40, number 28, page 52, number 5. Okay, so page 52, number 5. Consider the experiments in A and B of exercise 4. Okay. Okay, so for part A, we're just going to find we just draw 4 cards from a standard deck of 52. So we draw 4 cards from standard 52 card deck. Okay? So for part A, find the probability of drawing ace, king, queen, and jack of spades, and in that order in experiment A. Okay, so there's exactly 1 ace of spades, exactly 1 king of spades, exactly 1 queen of spades, and exactly 1 jack of spades. And so the probability of first an ace of spades, and then a king of spades, and then a queen of spades, and then a jack of spades. So the probability of that is equal to, well, the probability of an ace of spades is 1 out of 52. It's only 1 ace of spades out of 52 cards in the deck. That's times, now after you choose your first card, which is the ace of spades, there's only 51 cards left, and only one of them is the king of spades, so times 1 over 52, times, now there's only 50 cards left in the deck, and only one out of 50 is the queen of spades, so times 1 over 50, times 1 over 49, because only one of the remaining 49 is the jack of spades. And so you get the product of those 4 fractions, and that product is the probability. Okay, so that's part A. Okay, I don't really like that one. So let's keep going. Page 69, number 8. Okay. So there's going to be 5 cards. Alright, let's... Okay. So, page 69, number 8. So, number 8, in selecting 8 cards at random from a deck of 52 cards, what is the probability of selecting exactly 2 cards from each suit? Okay, so in a standard deck of 52 cards, right, you have the ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, and 2, right? And so those are the 13 different values. And for each of those 13 values, so these are your 13 different 13 values. And then from those 13 values, there's 4 suits, right? There's the spades, there's the hearts, there's the clubs, and there's the diamonds. Right? This is black. The spades are black, the hearts are red, the clubs are black, and the diamonds are red. Right, so half the deck is red and the other half is black. Okay, there's 13 spades, 13 hearts, 13 clubs, 13 diamonds. The spades are black, the hearts are red, the clubs are black, the diamonds are red. Okay, 13 red here, 13 red here, 26 and 26 black. Okay, so those are the 52 cards in the deck. For number 8, select 8 cards at random from the deck. So, and what's the probability of selecting exactly 2 cards from each suit? So the probability of 2 cards each suit. Okay, so well, so there's 13 spades, right? So 13C2 is the number of ways to choose 2 out of the 13 spades. Multiply that by 13C2, which is the number of ways to choose 2 out of the 13 hearts, times 13C2, which is the number of ways to choose 2 out of the 13 clubs, times 13C2, which is the number of ways to choose 2 out of the 13 diamonds. Okay, so now we've chosen 2 in each suit, and then divide that by the probability of the 52C8, which is the total number of ways of choosing 8 cards out of the total 52 in the deck. And so you calculate that, and that's the probability of 2 cards in each suit. All right? All right, so that's number 8. so okay, so I don't know. I numbered the problems. Okay, so let's do another problem. Okay, so let's go to page 106, number 2. Okay, so page 106, number 2. So for that problem, consider 3 flips of a coin. Use a table of values to find the following random variables. A, X is the number of heads minus the number of tails. And B, Y is the absolute value of the difference in the number of heads and tails. So let's make a table. And so here in the first column, let's just have the outcomes of the experiment. Okay, so the outcomes of the experiment are when you flip 3 coins, each coin is heads or tails. So the outcomes are heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. Okay, and so now for each outcome, X, this column, let X be the number of heads minus the number of tails. Okay, so that's going to be X. So that's for part A. And then for part B, Y is the absolute value of the difference of the number of heads and tails. So let Y be the absolute value of X, which is the absolute value of the number of heads minus the number of tails. Okay, so Y is just the absolute value of X. So X is the number of heads minus the number of tails. Is 3 minus 0, which is 3. 2 minus 1, which is 1. 2 minus 1, which is 1. 1 minus 2, which is negative 1. 2 minus 1, which is 1. 1 minus 2, which is negative 1. 1 minus 2, which is negative 1. 0 minus 3, which is negative 3. Okay, so that's the number of heads minus the number of tails for each outcome of the experiment. Okay, and now Y is the absolute value of X. So the absolute value of these numbers. The absolute value of 3 is 3, absolute value of 1 is 1, absolute value of 1 is 1, absolute value of negative 1 is 1, absolute value of 1 is 1, absolute value of negative 1 is 1, absolute value of negative 1 is 1, absolute value of negative 3 is 3. And you get that. Okay, and so this table answers both parts A and B. Alright. So that's page 106, number 2. Alright. Next problem. Okay, so page 109, number 6. Page 109, number 6. A box contains a penny, 2 nickels, and a dime. One penny, 2 nickels, and 1 dime. Okay? 1 penny, 2 nickels, 1 dime. If 2 coins are selected at random from the box, and X is the sum of values of 2 coins, what is the probability function of X? Okay, so X is the sum of values of 2 coins selected from the box. Okay? And so the goal is to find f of x, which is the probability that capital X equals some value little x. Okay. So that's the goal, to find the probability function, the probability that capital X equals some fixed little x. So the possible values of little x, so the possible values of, I guess, say capital X are So the possible sum of values of the two coins are either 1 penny and 1 nickel, which is in cents. So this is the sum of two coins selected from a box in cents, let's say. Okay, and so they are okay. So in cents, and so if you have 1 penny and 1 nickel, that's 6 cents. If you have 1 penny and 1 dime, that's 11 cents. If you then have 2 nickels, that's 10 cents. If you have 1 nickel and 1 dime, that's 15 cents. And those are the only possible values. The only possible values of X are these, okay? Right, so just to check, if you have 0 nickels, you have 1 penny, 1 dime, that's 11. If you have 1 nickel, exactly 1 nickel, then you can have a nickel and a penny, which is 6 cents, or a nickel and a dime, which is 15 cents. Then you have 2 nickels, which is 10 cents. Okay, so that's all the possibilities. So you could get these values by either saying you have 0 nickels, 1 nickel, or 2 nickels in the total 2 coins. All right? Okay, so the possible values of X are 6, 11, 10, and 15. And so you want to know the probability of each amount, getting each amount. All right? So, and so I'm going to put the outcomes of the experiment. And then I'm going to put the value of X here, which is the sum of the 2 coins selected. And so the outcomes are a penny. A P is going to be penny and nickel and D dime. So it's going to be a penny and a nickel, or a penny and a dime. And then it's going to be a nickel and a nickel, or a nickel and a dime. Those are the 4. So penny and nickel is 6 cents. Penny and dime is 11. Nickel is 10. Nickel and dime is 15. And so each of these totals have a 1/4 chance of happening, because each of these 4 are equally likely. And so f of x, which is the probability that capital X equals some little x, is equal to 1/4 if x equals 6, 10, 11, or 15. That's the probability function. Right? So the probability that capital X, the sum, is equal to either 6, 10, 11, or 15. Each of those 4 values is 1/4. And it's 0 everywhere else. Okay? But it's only defined for those 4 X values, so I could just say it. Alright? And so here we find the probability function of X. Okay, so that's another example. Let me check the camera real quick. Okay, that's good. Let's keep going. Okay, so page 130, number 2. Page 130, number 2. So prove that B of X and P is equal to B of N minus X and P. N minus X and 1 minus P. Alright, so prove that. Prove that that equals that. Proof. Let's start with the weirder one. B of N minus X and 1 minus P. And let's show it equals the less weird thing, the regular function. So this is N, choose N minus X, and choose N minus X, times the probability of success, which is 1 minus P here, raised to the N minus X, times the probability of failure, which is 1 minus this, 1 minus 1 minus P, raised to the total minus that many successes. Okay? So we want N minus X successes out of N, so it's N choose N minus X. then the probability of success is 1 minus p. And you're succeeding n minus x times. So it's 1 minus p raised to the n minus x. Then, if 1 minus p is the probability of success, then 1 minus p is the probability of failure. And so if you succeed n minus x times out of n, you fail n minus x times. And so it's 1 minus p, the probability of failure, raised to the number of failures, which is n minus the number of successes, n minus x. Okay, so let's simplify this. This is n, choose n minus x times 1 minus p to the n minus x times 1 minus p is p. That's p raised to n minus x is x. And so you get that. Now n choose n minus x is the same as n choose x. Okay? So for instance, if you have n choose a, that's equal to n choose n minus a. So here, so if you have n choose something, n choose n minus that something are the same. And so what we have here is that n choose x is equal to n choose n minus x. Instead of a is x. So n choose x is equal to n choose n minus x. So n choose n minus x is equal to n choose x, so I substitute. This is p the x, so I'm just changing the order, times 1 minus p the n minus x. And that's equal to the probability of x successes of n total Bernoulli trials, where the probability of success is p. So you succeed x times out of n, and the probability of success is p, so it's p to the x successes, times its failure, probability of failure, raised to the total number of trials minus the number of successes. Okay, so what I just showed is that this equals that, and so we proved it, and the proof is complete. All right? Good. So that's page 130, number 2. Page 137, number 2. So on page 137, number 2, we have this problem. If the probability that a certain book, it's an exercise. This is an exercise, not supplementary exercises. Okay, so for number 2 in the exercises on that page, consider a throw of 2 dice. Okay, so you roll 2 dice. Those are 2 dice. Right? The values are 1 through 6 on each dice. X is the sum of the values in the 2 dice. X is the sum of the 2 values. Okay, find and graph so let's just find the cumulative distribution function of x. Okay, right. So the cumulative distribution function, capital F of x, is the probability that capital X is at most some value little x. Okay, so what are possible values of the sum? Okay, so either x could be, the smallest sum is 1 plus 1, which is 2. It could be 3, it could be 4, it could be 5, it could be 6, it could be 7, it could be 8, it could be 9, it could be 10. It could be 11, and the most it could be is 6 plus 6, which is 12. So the possible values of x range from 2 through 12. Right, those are the only possible values of the sum of the 2 rolls of a dice, from 2 through 12. Okay, so the probability that capital X is at most little x, which is capital F of x, little x, is equal to, well, the probability that capital X is at most, if little x is equal to 2, then the probability that capital X is at most 2, well, that can only happen if you roll a 1 and a 1. That's 1 over 36. So there's only 1 out of 36 chance that the sum is at most 2, because there's only 1 out of 36 rolls, so 2 dice that give you a sum of 2, 1 and 1. 1/6 times 1/6, 1 over 36. Okay, now if x is equal to 3, then in addition to 1 and 1, which is 2, you could have, in addition to a sum of 2, you could also have a sum of 3, which is 1 plus 2 and 2 plus 1. So we add 2 more possibilities, so that's 3 out of 36. Okay, so there's a 3/36 chance that the sum is at most 3. There's 1 out of 36 chance it's at most 2 or equal to 2. And in addition to that, the sum at most 3 means it could also be 3. And there's 2 more possibilities to consider. The sum is at most 4. Then the ones to consider are when the sum is 4. And so that could be 1, 3, 3, 1, 2, 2. And so this was the original one. We added 2 more. Now we have 3 more. It could be 1, 3, 3, 1, or 2, 2. And so adding 3 more choices, you get 6 over 36. All right, 3 over 36 plus another 3 over 36 is 6 over 36. If x equals 5, then we could add values of 5 to this. So you could have 1, 5, 5, 1. Wait, sorry. The sum is 5. 1, 4, 4, 1, 2, 3, 3, 2. That's it. So you could add 4 more to that. And so 6 over 36 plus 4 over 36, you have 10 out of the 36. Alright, I'm going to extend this bracket a little bit more. If x equals 6, then we want the sum at most 6. And so we could do 1, 5, 5, 1, 2, 4, 4, 2, 3, 3. And so you could add those 5 also. So now you have 15 over 36 for the sum to be at most 6. Now for the sum to be at most 7, I'm going to continue here. The sum to be at most 7, we could add the sum equal to 7, which is 1, 6, 6, 1, 5, 2, 2, 5, 3, 4, 4, 3. And so now we add another 6 here. And so adding 6 to 15, or adding 6 over 36. So 36 there. So adding 6/36 more, you get 21 over 36. If x is 7. If x is 8, we can add sum of 8s. And so 1 and 6 doesn't work, so 2 and 6 does. So 2, 6, 6, 2, 3, 5, 5, 3, and 4, 4. So now we add another 5 over 36. That's 26 over 36. Now for a sum 9, we have sums of 9. 3, 6, 6, 3, 4, 5, 5, 4. There's 4 ways to get a sum of 9. So 4 over 36 more is 30 over 36. Now the sum could be 10, and if the sum is 10, you could either have 4, 6, 6, 4, or 5, 5. We could add 3 more. And so you have 33 over 36. If x is 10. And if x is 11, then I'm running out of room here, so I'm going to go over here. So for x equals 11, you have 5, 6, or 6, 5. There's 2 more. And so now it's 35 over 36. And if x is at most 12, then there's only 1, 6 and 6, which is 12. And so then you have 1. So 36 over 36, which is 1. All right? And that's it. And so that capital F of x, this is the cumulative distribution function for this random variable x, which is the sum of 2 dice rolls. Okay, so you see the pattern here. There's 1 simple outcome here, there's 2 more here, there's 3 more here, there's 4 more here, there's 5 more here. There's 6 more here, that's the most. That goes down to 5 more, 4 more, 3 more, 2 more, 1 more. Okay, so this is a pattern. Next one. Okay, so that's page 137, number 2. Next, we're going to go to page 150, number 2. Page 150, number 2. Okay, so number 2 on page 150. So let x, number 2, let x be a continuous random variable with probability density function. F of x is equal to negative 4x for negative 0.5 less than x less than 0, 4x for 0 less than x less than 0.5, and 0 elsewhere. Alright, so for A, sketch the probability density curve. Sketch the probability density curve. So negative y equals negative 4x could look something like that, but it's not. It's straight. Okay, so let's say this is negative 0.5, negative a half, and this is negative 4x between negative 0.5 and 0, and then it's 4x from 0 to 0.5. That's 0.5 there. Alright? And so this height is the value of 4x at 1/2, which is 2. The height of the function is 2 there. Alright, and so that's for part A. We're going to sketch the probability density curve. So this is the sketch of y equals f of x, defined on the interval from negative 0.5 to 0.5. Oh, and it's, okay, so that's 0 elsewhere. So actually it's going to include, it does include the rest of it. And so this part is also part of y equals f of x. This is an open circle. That's an open circle. It does not include the endpoints. It actually does not include 0 either, but then it's 0 everywhere else. So you don't include 0 for these two, but then you put 0 there for everyone. Okay, so that's part A. That's the graph of the PDF F. Part B is find the each probability. Find the probability that capital X is at most negative 0.3. So this is equal to the definite interval from negative infinity to negative 0.3 of f of x dx. Okay, and so this is equal to, well, if f is 0 everywhere less than or equal to negative 0.5, then we only care about starting at negative 0.5 to negative 0.3, right? The rest is 0. And so the graph there is negative 4x dx. Right? From negative 0.5 to negative 0.3, it lies in this interval. And so f is negative 4x throughout that interval. So you can plug negative 4x for f of x. And so the antiderivative of that is negative 2x squared. And so you evaluate it from negative 1/2 to negative 0.3. This is equal to negative 2 times negative 0.3 squared, which is 0.09, minus negative 0.5 squared, which is 0.25. So that's equal to 0.32. This is negative 0.16. The negatives cancel, so you get 0.16 times 2, which is 0.32. So the probability x is at most negative 0.3 is 0.32. Okay, that's number 2. Page 150, number 2, page 172, number 8. page 172, number 8. Okay, so let X be a standard normal random variable. Find the probabilities of each. Okay, sorry, hold on. Alright, I'm just going to use the book. Okay, so you have the thing online that gives you the tables for the standard normal distribution. Okay, so you can use the table on the site for that. So you want to find, so let X be a standard normal random variable. Okay, so let X be a standard normal random variable. Find the probability X will take on a value that is. So first for A, we want to find the probability that X takes on a value less than 1.5. All right. And so this is equal to the probability that X is less than or equal to 0, plus the probability that 0 is less than X, less than 1.5. The probability that X is less or equal to 0 is 0.5 or 1/2, right? Because it's symmetry. Probably X is less than 0, less or equal to 0 is 0.5. The probability X is greater or equal to 0 is 0.5. Okay, now this is given by the table that I provide on Blackboard. And so the table tells you that this probability is 0.4332. So you just do 0.5 plus 0.4332, and you get that equals to 0.9332. And so the probability that X is less than 1.5 is 0.9332. Right, so that's A. So for B, find a probability that X is greater than 2.14. The probability that X is greater than 2.14. Okay. So this is equal to 1 minus the probability that X is less than or equal to 2.14. And that's equal to 1 minus the probability that X is less than or equal to 0, plus the probability that 0 is less than X, and less than or equal to 2.14. And the equal sign doesn't matter here. We can get rid of it and say strictly less than. Right? The probability that X is any particular point is 0 is actually a continuous random variable. Okay, so let's close the bracket there. So the sum of this and this is the probability of that, but it's minus that probability, so it's minus the sum of those two things. This is equal to 1 minus the probability that X is less than or equal to 0, which is 0.5, minus this probability. And the table tells you that probability is 0.4838. 0.4838. Okay? And so that's 1 minus 0.9838. And that's 0.0162. Good. Okay, so that's part B. Next. Okay, so part C, number 8. The probability that X is between 1.5 and 2.14. Okay, so that's equal to the probability. So this is equal to the probability that 0 is less than x, less than 2.14, minus the probability that 0 is less than x, less than 1.5. Okay, so the probability that x is between 1.5 and 2.14 is the probability between 0 and 2.14 minus the probabilities between 0 and 1.5. And so the table tells you each of those. And so the table tells you this value is 0.4838 minus that probability, which is 0.4332. Point 0.506. Okay, so 0.438 minus 0.332, 0.4332 is 0.0506, and that's the probability x is between 1.5 and 2.14. So that's part C. Okay, so that's part C. Okay, so having practice with this one, let's do one more. Okay, so part D of this problem, we want to find the probability that x is a value less than negative 1.32. So the probability that x is less than negative 1.32. All right, so this is equal to the probability that x is less than or equal to 0 minus the probability that negative 1.32 is less than x, less than 0. Okay, so the probability that x is less than negative 1.32 is the probability that it's less than or equal to 0 minus the probability that it's less than 0 and greater than negative 1.32. And so this is equal to 0.5 minus that. Now, there's symmetry, which means you can, instead of going from negative 1.32 to 0, you can say it's the probability from 0 to 1.32. Okay? And so this is equal to 0.5 minus that probability, which the table tells you is 1.32, which is 0.4066. Okay, which is 0.0934. So that's equal to 0.0934. Okay, so that's the probability for part D. Okay, so let's go to another problem. So let's do another problem. Okay, so that's 172. Next is page 175, number 5. No, page 175, number 3. Okay, so for number 3, it says find the cumulative distribution function of the continuous uniform random variable. And it says the PDF is given in definition 5.3, right? So the continuous uniform random variable is f of x is equal to, let me look at this, their definition 5.3. Make sure. Okay, so f of x is equal to 1 over beta minus alpha for alpha less than x less than beta and 0 elsewhere. Okay, so here alpha and beta are constants. Alpha is less than beta. So we want to find the cumulative distribution function of x. And so capital F of x, which is the probability that capital X is at most little x, is equal to the definite integral from alpha to little x of 1 over beta minus alpha dt. And so finding the probability that x, that capital X is most little x, is just integrating the probability density function from alpha to x. Okay, the graph of this continuous function is, the graph of this is, let's say this is alpha, this is beta. Then the value of the function is 1 over beta minus alpha on that subinterval. It's just the height of it there. So that's the graph, right? Very simple. And so if you want to find the probability that capital X is at most little x, let's say little x is there, then the area of that is the probability that capital X is at most little x, is integrating that function from alpha to x. Okay, and if you integrate that, you get 1 over beta minus alpha t, evaluated from alpha to x. And that's equal to x minus alpha over beta minus alpha. And so this is for alpha less than x less than beta, less than or equal to beta. Include alpha too. Okay, so this is for x between alpha and beta, including alpha and beta. Right, if x is beta, you get beta minus alpha over beta minus alpha, which is 1. You get the entire area there. And if x is alpha, you get alpha minus alpha over beta minus alpha, you get 0 over non-zero. 0. Okay, so the cumulative distribution function is x minus alpha over beta minus alpha for x between alpha and beta inclusive. So that's number 3. Okay, next one. Page 175, number 3. Page 182, number 4. So page 182, number 4. All right. If a set of 3 bowls is selected at random from a box containing 10 bowls, 4 are white, 6 are black. What is the expected number of black balls in the set of 3? So we're going to choose 3 out of these 10 balls, and what is the expected number of black balls? So the expected number of black balls, if we're choosing 3 from the box. Okay, that's the box. Okay, and so the expected number of black is the number of balls I'm choosing, which is 3, times the probability of choosing a black, which is 6 out of 10. So 3 times 6 over 10, that's 18 over 10. That's 1.8. So the expected number of black balls you'd expect is 1.8 on average. So on average, if you choose 3 balls from this box and 6 are black and 4 are white, on average, in the long term, you choose 1.8 that are black. All right? You're rounding. So you're taking the average. I mean, not rounding. You're taking the average. And so the average of the number of blacks you choose with a lot of experiments repeated is 1.8. Okay, so that's page 182, number 4. Next problem. Page 193, number 1. Okay, so page 193, number 1. If player A pays player B $1 when the outcome of one roll of a die is a 1, 2, 3, 4, or 5, then in order to make this a fair game, what should player B pay player A when the outcome is a 6? Okay, so this is what happens for 1 through 5, and that's what happens for 6, and we have an unknown amount, X dollars, that B gives to A in that situation. We want this to be a fair game. What a fair game means is that the expected value is 0. Okay, so 0 is equal to the expected value. And the expected value is equal to, let capital X be the amount A gives B. Okay, so the expected value is that there's a 5/6 chance that A gives B $1, plus a 1/6 chance A gives B negative X dollars. Okay, so why? Because the problem is saying what should player B pay player A? So if I want, so capital X is the amount A gives B. Little x is the variable little x, so that's so confusing, is the amount B pays A to have a fair game. Okay, so in this case I want to talk about how much B would give A. The capital X is the amount A gives B, right? And so here I want to talk about how much A gives B. And so if little x would be the amount B pays A, then the amount A would give B is negative x, negative little x. Okay, so we're going to solve this equation for little x here. We get 0 equals 5/6 times 1 plus 1/6 times negative x. And so you get x times 1/6 is equal to 5/6. And multiplied by 6, you get x equals 5. And so the amount B pays A to have a fair game is $5. So the answer is $5. In dollars. Okay? And just defining X. The amount A gives B in dollars. So the answer is $5. Okay, so that's that problem. Let's continue. Page 199, number 2. Okay, so page 199, number 2 is let x be a random variable with probability function given by f of x, which is equal to 0.1 for x equals 1, 0.4 for x equals 4, and 0.5 for x equals 9. Find e of x squared, and among other things. Let's find e of x squared. Okay, so e of x squared is equal to the sum over all possible values of x squared times f of x. And so that's equal to, these are the 3 possible values of x. So when x is 1, you get 1 squared times f of 1. And plus when x is 4, 4 squared times f of 4. Plus when x is 9, 9 squared times f of 9. That's equal to 1 times f of 1, which is f of 1, which is 0.1. Plus 16 times f of 4. So you get 16 times f of 4, which is 0.4, plus 9 squared, which is 81, times f of 9, which is 0.5. And so this is equal to 0.1 plus 0.64, 6.4 plus 40.5. And so this is 46.9 plus 0.1, so it's 47. Okay, so the e of x squared is 47. Okay, so e of x squared is 47. Let's do one more. Okay, so now let's find e of x to the 1/2. See, e of x to the 1/2 is the sum of all passive values of x to the 1/2 times f of x. Okay, so if this is when x is 1, you get 1 to the 1/2 times f of 1. Plus when x is 4, you get 4 to the 1/2 times f of 4. Plus when x is 9, you get 9 to the 1/2 times f of 9. So that's equal to 1 times f of 1, which is 0.1, plus 4 1/2, that's the square root of 4, which is 2, times f of 4, which is 0.4, plus 9 to the 1/2, which is 3, times f of 9, which is 0.5. And so this is equal to 0.1 plus 0.8 plus 1.5, and that's equal to 2.4. Okay, and so there's a third one, but it's just very similar to the first two I did, so I think we're good here. So let's go to the next problem. Okay. Page 209, number 1. So number 1, page 209, is let x be a random variable with e of x equals 1, and e of x times x minus 1 to equal 4. Find the variance of x. So let's find the variance of x. Okay, so the variance of x is equal to e of x squared minus e of x. I'm just going to exaggerate. That's e of x squared. The notation you could also write is e squared of x. That's the square of e of x. Okay. Sorry, the markers are weird. All right. So let's find e of x squared minus e squared of x, or e of x squared. Well, this equation tells you that e of x times x minus 1 is equal to, this is a new marker, which is why it's not there. Okay, so this is e of x squared minus x. That's e of x squared minus e of x. That's equal to 4. Okay, so what does this tell you? It tells you that 4 is equal to e of x squared minus e of x. So that means that e of x squared is equal to e of x plus 4. Right? If we solve for, if we add both sides by e of x squared is e of x plus 4. Well, we're given that e of x is 1, so this is 1 plus 4, which is 5. So e of x squared is 5. Okay, so this is equal to e of x squared, which is 5, minus e of x, which is 1 squared. This is 5 minus 1, which is 4. So the final answer is 4. All right, so the variance of x is 4. Okay, Okay, so we have that the variance of x is 4. So I'm going to write this over here so don't forget. Okay, now let's find something else. Now we're going to find the variance of 2 minus 3x. Okay, so what is the variance of 2 minus 3x? Well, there's a formula that says the variance of ax plus b is equal to a squared times the variance of x. So in this case, this says this is the variance rearranging the terms of negative 3x plus 2. The negative 3 is the a, not the 2. Even though the 2 is in front here, the 2 is the b, the a is the negative 3. A is negative 3, b is 2. So this is equal to negative 3 squared times the variance of x by this equation, right? This is equation star. And so that justifies this equality. Okay? Well, that's negative 3 squared is 9. So it's 9 times the variance of x. And we found the variance of x was 4 already. So this is 9 times 4, which is 36. So the variance of 2 minus 3x is 36. Okay? So there's that problem. The next one is page 215. So we have page 215, number 2. Okay, so page 215, number 2. Suppose the probability of a certain football team wins a game is p equals 0.7. If the team plays 15 games, what is the expected win? What is the expected wins? Okay, so the expected number of wins. If the probability of a win is 0.7 and there's 15 games, the expected value of the number of wins, the expected value of wins is the number of games 15 times the probability of winning each game, which is 0.7. And so that's 1 point. So that's 13.5. 15 times 7 is 105 decimal. 15 times 7. It's 105. One decimal place. It's 10.5. Okay, so the expected number of wins is 10.5. That's it. So that's 215, number 2. Okay, so we went over a lot of problems, and so hopefully this is somewhat helpful. Okay, let's do another example. Page 219, number 1. But number 1, let's do part D. Okay, so if x is a random variable having a normal distribution with mean u equals to 2, and standard deviation sigma equals 0.5, find the probability that x takes on a value, find the probability that x takes on a value less than 1. Okay, so x is a normal random variable. It has a normal distribution. It's a normal random variable. It's not a standard normal random variable. The table that I gave you is for a standard normal random variable. So we have to convert this x to a standard normal random variable. So we can do that. Probability that x is less than 1 is equal to the probability that x minus mu over sigma is less than 1 minus mu over sigma. And that's equal to the probability that z is less than 1 minus mu, which is 1 minus 2 over sigma, which is 0.5. So here z is x minus mu over sigma. Z is a standard normal random variable. Okay, so this is how you convert your normal random variable to a standard normal random variable. And so this is equal to the probability that z, your standard normal random variable, is less than 1 minus 2 over a half. That's negative 1 over a half. That's negative 2. So probability z is less than negative 2. Okay? Well, that's equal to the probability. That's equal to the probability that z is less than or equal to 0 minus the probability that negative 2 is less than z less than 0. And that's equal to, this is 0.5 minus, because of symmetry, this is minus the probability that 0 is less than z less than 2. Z is a standard normal random variable, and you can use the table for a standard normal random variable. It's not enough for normal, you need a standard normal. Okay, so applying the table to this situation, you get that the probability is 0.4772. So the probability that z is between 0 and 2, where z is a standard normal random variable, is 0.4772. So 0.5 minus that is 0.02 to 8. All right, and so that is the probability that x is less than 1 in part D. Okay, so that's page 219, number 1. That's another review problem. Okay, so it's page 219, number 1. All right, so we'll stop here. Okay, so keep doing problems. Go over the homework, other stuff. The more problems you can do, the better you'll know the material. All right, so good luck studying, and have a good day. Bye.